Right. This lesson, I am going to look at some information for paper 3, but it also turns up in paper 1 and 2. It is about analysis. It is about testing for cations and testing for anions. Cations are the positive ions, anions the negative ones. Sometimes in a paper 3 practical, you are told to do some mixing of chemicals and you are expected to write down your observations and then write an equation or an inference. So that's what this one is about. But there were two questions last time that I didn't finish. So I want to just look at those. They were, well, we will see in just a moment. So I am just looking for. Ah, yes. Here's the question. I will make it a bit bigger. This was one I mentioned it last time. We had a brief look at it, but I want to look at it a little bit more so that you can recognize what we are talking about. This is quite a common question about hard water. Now, hard water is water that contains Ca2 plus or Mg2 plus ions. Okay. Uh, so hard water is water that contains those ions, either calcium or magnesium ions. And they can interrupt or stop soaps working properly. They quite often have a question like this, in which you are looking for what we think of as the functional group. Forget about all of the rest of the molecule. Like this bit is unimportant, unimportant. The bit which is COONA, this is a soap. Okay, that is a soap. Every time you see that, this is the sodium salt of an alkanoic acid. They are very long alkanoic acids. They are called fatty acids, but that's a soap. Whereas this here, if you look at it, this looks like a sulfate, COSO3, with the R group, the bit of the organic molecule, that's this, and then Na. And this is a detergent. Now, there is a lot of difference between a soap and a detergent. Both of them are used for washing you, for washing clothes, for washing paper, all sorts of things. But a soap is much cheaper than a detergent because a soap is made from basically taking a fat or an oil and adding sodium hydroxide. And that's about it, really. A bit of cooking, but otherwise it's made that way, whereas detergents are more expensive. So both of them will be quite good for cleaning things, but there are disadvantages. So I'm just going to tell you about the disadvantages. So it says here, which cleansing agent would be more suitable for washing in water containing magnesium sulfate? Now, magnesium sulfate, because it's got magnesium in, because the magnesium is here, that makes it hard water. Now, hard water reacts with soap. So I'm just going to show you what happens. Let me just, oops, why can I not do that? Okay. So I'm just going to get rid of all the bits which are unimportant now. Okay. Now what happens is this. If I have this part of the molecule and I add magnesium ions, the magnesium ions swap for the sodium. So the sodium goes, let's get rid of the sodium. and the magnesium joins on here. Now, actually, we need two of these so that we've got R here, and we have another one here, which joins on like this, like that. But this here is what we call scum. This is white precipitate. If you wash your hands with soap and it is hard water, you will get some insoluble chemical, which is this magnesium salt of the alkanoic acid. When it reacts with this part of a detergent, although it does swap for the sodium, so we get magnesium on there, this is still soluble. Okay, this is still soluble. So which cleansing agent would be more suitable? B, explain why. So the magnesium ions I'm not going to write this. Oh, sorry. I'm not going to write this in full sentences. The magnesium from the magnesium sulfate makes it hard water, and the Mg2 plus reacts with A, and A is a soap, to make scum, which is no good. It will not make bubbles until the scum until all of the hardness has gone. So if you take some soap and hard water and you rub it, nothing happens at all. You don't get any bubbles to start with. And then as you wash and wash and wash and wash, you get more scum, and then suddenly you get bubbles. And that is because all of the magnesium or the calcium has gone. Okay? But so it only happens when all the magnesium or calcium has reacted. Okay. I hope that makes sense. Is that okay with everybody? Just give me a thumbs up if that is okay. Is that okay, Dandora? Thank you again, Dandora. Thank you, St. Mary's. Thank you, Mathari. That's great. Well done. So all you have to do is to remember that and to remember which one of these is which. So this is the one that you have to sort of get used to recognizing. Kuna soap. Okay? Kuna soap. This one here, detergent. So it is always, this is the sodium salt of COOO. You should recognize that was an alkanoic acid. So it is now an alkanoic acid salt, and that is the soap. Okay, next question. Here is very similar because this is about the same reaction. So this shows either a fat, this is a fat, but it could be an oil. And what I want you to do is recognize something, and that is this bit of it. Whoops. There. If you look, we have COO again. That is an alkanoic acid again. So this, when it reacts with sodium hydroxide, forms these, which are that there. That tells you it is a soap. So the type of compound is a soap. If you want to be very specific, you can say sodium salt of, and we call these a fatty acid. Okay, we call them a fatty acid. And the use is cleansing or cleaning or washing hands or whatever you want to say. Okay. The other question, which I didn't do, which is what is vulcanization of rubber? Now, rubber as a normal chemical is a hydrocarbon with lots and lots of long chains. And these long chains are very, very flexible. And they can move over each other as well. So they are just like if you had a pile of sticks, they can slide over each other. And it is the same with this. And that makes rubber very soft. When we vulcanize it, we heat the rubber with sulfur. And what the sulfur does is, I'm going to look at one little bit of this, so I'm going to make this bigger over here. Here's one chain and here's another chain, and the sulfur attaches between the chains like this. And it does it quite often. So there are lots of what we call cross links. That's links between the rubber chains. Okay, so there are lots of them. So they are, excuse me. So this makes, now if you want to be really clever, you can call it disulfide, which is what it is. Cross links between chains of rubber. Now that's really quite important. Let's just get rid of all of this for a minute. Now what that does is it means that now the rubber chains cannot move over each other so quickly. And so when it says state two properties that vulcanized rubber possesses, is it is stronger because the cross links help to hold them together. It is less flexible. It is also harder. Now, harder sounds a little bit like stronger, but it's not really. And we use vulcanized rubber for bicycle tires, car tires, lorry tires, and so on. And the idea of that is that it's not going to wear down so quickly. It is a little bit less sticky. I do rock climbing, climbing cliffs, and the boots that we use have rubber with almost no vulcanization. That is so it is stickier, so it sticks to the rock, whereas and so they wear down fairly quickly, but that makes them sticky, and so it is always a balance between the strength and the stickiness. So vulcanization, heating with sulfur, and it makes it harder and more hard wearing. So the car tires or lorry tires do not just break, which is good because you don't want them to just break. Okay, so let's move on. So now we're going to move to today's lesson. Whoops. I wasn't sure whether everybody is everybody happy about hard and soft water? Just show me with your thumbs, please. Are you okay on hard and soft water or not so okay? Most people okay? Yes. Okay, great. Thank you. So I won't bother with that slide. Okay. So we're going to be looking at identifying ions. I'm going to send this presentation to your teachers so they can show you this if they want. And it contains some quite interesting things. I'm going to just show you this because it's to me it is interesting. It is something you don't need to know about, but I'm just going to show you a little bit of it. What we have here is a group of beakers, and they are going to be lit. They have ethanol and alcohol in them and various chemicals with it. And this is to show you that different chemicals give different colored flames. Now, you may know that from fireworks and so on, but this shows you that to start with, they all look fairly similar. But as they warm up, they make different colors. And we can use these to identify the metal which is in them, or non-metal sometimes. So for instance, this one is going quite red, and that is lithium. Now I'm going to just stop it for a minute and just tell you something. If you were in a practical, paper 3 examination, and you thought something contained a particular chemical like sodium, if you could put it into a Bunsen flame, the color would show you what the chemical is. So this color red, mainly red, is lithium, mainly yellow orange is sodium. Boron, a non-metal, produces a nice green. Copper gives you a brilliant green and blue at the same time. So these flames are all just like that. Here they are, different colors for different metals. Okay, let's move on. Okay, so this is the one which they ask you to know most about, which is the precipitation reaction for cations. And if you were here when I was talking about electrolysis and electrochemistry, I told you if you write cation with a plus instead of the T, you will always remember cations are positive. All right. There are two sets of reactions you need to know about with sodium hydroxide, with ammonium hydroxide. So we are going to look at those two now. Okay. So here we have a series of tubes with chemicals in it, and I'm not going to tell you what's in them to start with. Each one of them is a solution, and sodium hydroxide is going to be added to them. If you are asked to do this in the examination, you will be asked to add a few drops and then sometimes excess of the chemical. So let's see what happens. So this one is colorless so far, as much as we can tell. And let's add a few drops of sodium hydroxide to it. Any color, any precipitate is important. So let's see what happens. Oops, something stopped. Why have you stopped? Oh, there we are. We're going again. Okay. So here you may be able to see some cloudiness forming. Now that cloudiness is green. And that green tells me something. Let's add a little bit more. Add a bit more, please. But that green precipitate, and you can write precipitate just as PPT, you probably know this. That green precipitate tells me that this is Fe2 plus, iron 2 plus. There it is, spread out a bit more. It is quite a dark, it is sometimes described as dirty green precipitate. The next one starts as a yellow solution. Let's add some sodium hydroxide to that. As I add sodium hydroxide, sometimes it takes a little bit for anything to happen, but this one is producing a rust-colored precipitate, a red-orange brown precipitate, and that shows Fe3 plus. Fe3 plus. So Fe2 plus on the left, Fe3 plus on the right. A blue solution is almost always copper. Let's see what happens with copper and sodium hydroxide. With sodium hydroxide and copper, you probably know this, but you get a really rather beautiful, very pale blue. Add the sodium hydroxide, please. Come on, there we are. Pale blue precipitate. This one looks more jelly-like. It is quite strange. It is the other two are more, although it doesn't look like it here. In this one, it is more like dust. This one is a bit more like jelly, but this one is really like jelly. So Fe2 plus, Fe3 plus, Cu2 plus. Now, sometimes you get something happening which is a bit annoying. So for instance, these three all produce a white precipitate. And so what we need to do is to find out a way to tell the difference between them. Now, this one is zinc, and these two are aluminium and lead. Okay, this is zinc. And what you need to know about zinc is that if you add a lot more, if you add excess, then something happens to it. You need to add quite a lot more. And sometimes you have to just look at it and go, yes, has it got less or not? So we are going to add some more sodium hydroxide to the zinc now, not to the aluminium and lead. It's called excess. Come on, chemist, get on with it. And it starts by just thinning out, getting thinner like that. You can see if we mix it properly, that still has a white precipitate. We need to add some more. We need to add some more. I don't know if you can see there, but there is still a thin white precipitate in there. There, that is better. More sodium hydroxide, and it completely redissolves. Okay, so dirty green precipitate, Fe2 plus, orange precipitate, Fe3 plus, blue precipitate, Cu2 plus, a white precipitate which dissolves sodium hydroxide, that is zinc. The other two are aluminium and lead. Let's move on. Now let's add ammonium hydroxide to them. Let's add ammonium hydroxide to them. Again, we've got almost colorless. That one is slightly blue. Let's add ammonium hydroxide to them and see what happens. So here's ammonium hydroxide. There is the green precipitate. That means that is iron 2 again. This blue, that means copper 2. This orange means that it is iron 3. Okay, this white, we are not sure what it is to start with. If I add excess to the iron 2, nothing changes. If I add excess to the copper, something strange happens. It disappears. The precipitate disappears and it goes to dark blue. If I add excess to the iron 3, it's still cloudy. You can see there are still bits in there. No real change. If I add it to this one here, no change. Okay. So when I send this to your teachers, you can use the next one to test yourself if you want. You can try to predict what is going to happen, and you can try to write the equations, which is what we are going to do next. Here it is. This is it. So for instance, this first one, a pale yellow solution of Fe3 plus, add sodium hydroxide to it, what will you see? And so on. So you can do that yourselves. This is a textbook page of what you need to know, but this is really quite hard. There is too much information here. So what I'm going to do is to simplify it. And we're going to look at when there is no white precipitate, when there is a white precipitate which is soluble, when there is one which is insoluble, and so on. So let's make it a little bit easier. So if you want to draw out a table to record what happens, I'm going to have no precipitation is the observation, a white precipitation which is dissolving in excess, and one which doesn't dissolve with sodium hydroxide with ammonium hydroxide. So that's what I'm going to do. So let us imagine that we are adding sodium hydroxide to a solution. If there is no precipitate, then it is one of these three. It is a group 1 metal or ammonium. Okay, K plus, Na plus, NH4 plus. If there is a white precipitate which dissolves in excess, zinc, aluminium, or lead. Zinc, aluminium, or lead. Now, these are often described as the amphoteric metals. And some teachers ask you to remember ZAP, zinc, aluminium, and P for plumbum for PB. Okay? So that's what's happening there. And if we have a white precipitate which does not dissolve, then it is group 2. So group 1, no precipitate. Group 2, white precipitate which does not dissolve. White precipitate which does dissolve, this is with sodium hydroxide, amphoteric. Okay, so far. So let's have a look at what happens with ammonium hydroxide. Slightly different. There's the results for sodium hydroxide. Here it is for ammonium hydroxide. If we get no precipitate at all, it might be group 1 or ammonia or calcium or barium. Now that's quite important. That's different from sodium. If it is white precipitate which dissolves in excess, this is great. It is only zinc. If it does not dissolve in excess, then it's aluminium or lead, the other two from ZAP, or magnesium. So let's look. Let's make sure that everybody knows that. It's important that you know this and you know this. Okay, you need to know them. You need to remember them because this is what they ask sometimes in paper 3 and also in paper 1 or 2. So I'll just go back. I'll show you for sodium hydroxide. Here they are. No precipitate, group 1 or ammonium. White precipitate which does not dissolve, group 2. White precipitate dissolves, ZAP. In ammonium, slightly different. Here we are in ammonium. Group 1 or 2, except magnesium. Okay, group 1 or 2, except magnesium. Dissolves in excess only zinc, not the other two from ZAP. The white does not dissolve. The other two, AP, not ZAP anymore, and magnesium. Let's look at the equations. So let's have a look at the equations which we need to be able to write. So the first one, in no precipitate, there is no point in writing an equation. Nothing happens. We could write, let's say it was sodium, we could say Na plus AQ plus OH minus AQ goes to NaOH AQ, except that NaOH AQ is actually Na plus and OH minus. So that is useless. It is not worth remembering. Okay, so just don't even write equations for that. Okay, so let's now write it for a white precipitate. I'm going to do the simplest one, which is at the bottom. The white precipitate which does not dissolve in excess, and we said that was group 2. So let's have a look at, let's say, magnesium. So Mg2 plus, we always write plus OH minus. And then all you have to do, whatever the precipitation is, it will have the same number of OHs as the charge on the metal. So we will have 2 here. And that means I needed 2 here. Now this was AQ, this was AQ, and this is solid, showing that it is insoluble. Now, exactly the same thing happens at first here because they get a white precipitate. So let's take zinc. So I take zinc and I add OH minus, and because it's 2 plus, I will need 2 of these to make ZnOH2 as a solid. That's the first bit. That's the white precipitate, which I get at the beginning. What happens next is this. ZnOH2 has more OH minus added to it. And it is the same in all cases. And that is that it takes two more to become four. Now, because this is not charged, and because each of these two which I'm adding to it, this is now going to be 2 minus. But instead of leaving it there, we put this in square brackets, which means it is what we call a complex ion. In other words, the whole charge, the charge is written over the whole thing. Okay, that it is shared over the whole thing. So that's the two equations you need to be able to write. So this, the first one here, that is the white PPT, and this is the dissolving again. So this is going to be AQ again. So let's see if you can do that. Let's see if you can do that. Okay, so I'm going to give you a moment just to write that one down in case you want to, and then I'm going to ask you to write two more equations. These are about to disappear. So if you haven't written them down, you might want to now. Here they are, they're going. Uh-oh, look, oh no. Don't do that, sir. Yes, the teacher is getting rid of what you will need in just a moment. Oh dear. They're all disappearing. Oh no, please don't do this. Oh dear. Uh-oh, gone. Okay, so what I'm going to ask you to do now is I'm going to ask you to write equations for two other chemicals. So, whoops. Here we go. So what I would like you to do is to write an equation for magnesium ions here in the ones which do not dissolve in excess. And up here, I would like you to write it for aluminium ions, which do dissolve in excess, but need to have a precipitate first. So I'd like everybody to try to do that first, okay? Just to write those two equations, because if you can do those equations, that would be excellent. I would do the lower one, the magnesium one first. It is easier. Kabira, you're a really long way away. Kabira students obviously don't like chemistry very much. Really good work from St. Mary's and Kabira and Dandora and Mathari. One set of Kabiro anyway. Come on, Kabira, let's see you writing. Ah, Kabira, they've lost the power of, they don't have a pen. Excuse me, teacher, could I borrow a pen, please? I don't have a pen. Oh, now I don't have paper. This is terrible. Ah, excuse me, teacher, I cannot do the examination. Why not? I don't have a pen. I used to go to chemistry lessons, but I could not practice because I didn't have a pen. Hang on just a moment. I'm just going to have a look. A little bit closer, please, Brian. The first one is right. The second one is not quite right. Have a look. Because aluminium is 3 plus, you need to work it out so that it balances and becomes not charged. So you need the right number of OH minuses to make it not charged. Kabira have found a book and a pen. Wow. Excellent. Well done. Thank you, Brian. Yes, look. Yes, I know. I know it's a pen. Well done, Kabira. Yes. Now, what you've got to try and do is to use the pen and the paper to write the equation. Oh, no, that's too difficult. Dandora girls have gone. That's a bit of a shame. That's a bit of a shame for Kabiro because now I can see Kabiro more. Okay, so we're going to check this. We're going to check and see if people have got this right. So here we go. So Al3 plus, sorry, Mg2 plus will be plus 2OH minus. It's very important that you check this each time because it's about that. So whatever the cation is, we need to balance the charges. So this is going to become 2 here, and that is then a solid. This was a Q. This was a Q. So that's a white precipitate which does not dissolve. How about aluminium? Well, aluminium is one of those with oops, sorry, I'm on the wrong slide with ammonium hydroxide. With sodium hydroxide, aluminium does dissolve. So it will be plus, because it's 3 plus, 3OH minus becomes AlOH 3, and that's a solid. Then the AlOH 3 has one more OH minus added to it to make AlOH 4. Put it all in square brackets. Every time it dissolves, put it in square brackets there. And now the charge on this one, well, I've got 4 OH minuses. So each one of those is minus, and this was 3 plus. So the whole thing is 1 minus AQ. So this was a solid. That's the white precipitate. That's AQ. And there we are. Okay, let's just get rid of that. I hope that's okay. Let's just see that that's okay for people at the moment. Whoops. Is that okay so far? Good. Thank you, Mathari. Kabiro? Okay, good. Excellent. Oh, some people behind, not quite so. Dandora, not so happy. St. Mary's okay. Wamwini, is that okay? Not so good. Okay, we'll look at it again. We'll have a look at it again. Hang on. Let's get rid of what we have at the moment.
Excuse.
Hello?
Does aluminum form a complex ion?
It does.
Okay, thank you.
With sodium hydroxide, not with ammonium hydroxide. Right, hang on. Where am I? Okay. So we said with no precipitate, there is no point in writing an equation. So we're writing, oops, sorry, I'll just get rid of these equations. We will do them again. I might, hang on, I will just go to a completely blank side. Let me just put in a blank slide here. Okay. Okay, so if we get a precipitate, so we are saying, yes, we have a precipitate with any hydroxide. So any OH minus is added. Okay, it doesn't matter whether it's sodium hydroxide, potassium hydroxide, calcium hydroxide, ammonium hydroxide. It doesn't make any difference. If we get a precipitate, this is what happens. So let's say we are looking with Mg2 plus. Then we look at the charge here, 2, and we go, I need 2 OH minus. That's because if it is going to be a precipitate, it has to be not charged afterwards. So this is not charged because that's 2 plus. And this is two minuses, so there's no charge. And then it becomes solid. So if we had something which forms, for instance, silver does the same. If we had something which was Ag1 plus, then it would go with one OH minus and it would make AgOH, no charge, solid. If it is something with a 3 plus, like aluminium, then 3 plus, 3OH minus, AlOH3 solid. If we could do it with lead 4 plus, then it would be plus 4OH minus, and that would make PbOH4 solid. So whatever it is, every single time you just look at the charge, that's the number there, and that's the number there. I hope that's clear. Okay, so let's just go now for when we get the precipitate and it now dissolves. So I'm now going to get rid of those. So this time I OH minus excess added. Okay, so we're adding excess to the precipitate which we have already formed. In other words, like zinc, I have already made ZnOH2. So if it dissolves, then what is happening is that the precipitate there has more OH minus added to it, and it always forms OH4. Now, some people will tell you that is not true. And if you are going to go on and do chemistry at university, you would find that they will tell you sometimes it is 6, sometimes it is 2, and so on. But we are going to remember 4. The charge which I get depends upon the charge here. So this was 2 plus, okay? And there are 4 of these which are 1 minus each, so it's 4 minus. So the whole thing goes in square brackets. And then my total charge will be 2 minus. And now because it is charged, it will redissolve. So the nice thing about this is that, let's say I want to change this to, let's say I'm trying to do it for something else. I'm going to give you something which you don't need to know about. Okay, I'm going to start with chromium, because chromium is also amphoteric. So in this case, I would get chromium here and chromium here. It's exactly the same. Okay, because it's chromium, because this chromium is 2 plus and amphoteric, therefore it would do this thing. If it was aluminium, then aluminium starts as AlOH3. So we're going to add OH. Oh, I'm sorry. Look, I needed 2 there. My apologies. I need 2 there, so I get 4 altogether. So here I'm going to make the same basic chemical, Al with 4 OHs, square brackets. And now, because that is 3 plus, and this is 4 minus, this is just going to be 1 minus. Oops, just 1 minus AQ. And therefore, I only need one of those. Is that okay? Is that okay? Dandora, Mathari, St. Mary's, does this make sense? Kabiro, yes? Cool, excellent. Okay, let's move on. go back to sharing. Okay. Now, sometimes we get colored precipitates. As we saw in the little test tubes, which I showed you, sometimes we get colors or sometimes we get gases. Okay. Sometimes colors or sometimes gases. And we saw them, and here they are. Here are the results. And they are much easier to remember than the other ones because they are colored. So anytime it is blue, it is copper, copper 2. Anytime it is green, it is Fe2 plus. Anytime it is orange, it is Fe3 plus. And I'll come to ammonium in just a minute. So Fe2 plus and Fe3 plus, they only produce precipitates. The precipitates are not soluble later, okay? So I'm going to give you a chance just to write an equation for one of these. So what I'd like you to do is just write an equation for this precipitate forming. This is with sodium hydroxide and iron 2. Okay, just write an equation for iron 2 and sodium hydroxide. Just see if we can do that. Iron 2 and sodium hydroxide making a green precipitate. Fe2 plus sodium hydroxide. Write an equation. Can somebody show me an answer? Go on, Dandora, you can do it. Go on, have courage. You're almost completely right. Just look at how many OH minuses you have added. Just look at balancing the equation. You see it? Yeah, you got it. So this is correct. Well done. Very good. So this would very simply be Fe2 plus AQ plus, because it's two of them, 2OH minus AQ goes to FeOH2 solid. That's it. Okay, that's the one. Good. Now there are just two on here which we haven't dealt with. Okay, there's two on here which we haven't dealt with. The first one is this up here. This here. Now, this is different from what happens with sodium hydroxide. If something dissolves with sodium hydroxide, what we get is something with 4 hydroxides around it, but copper is different. So let's look. Here's Cu2 plus 2OH minus makes the pale blue copper hydroxide precipitate. But when it dissolves in ammonia, something completely different is happening. And this is very important. Whoops, something funny is happening with my pen. So I get my CuOH2 and I add ammonium hydroxide to it. Now, it's actually this, but it's okay to write ammonia, because what forms is a different complex altogether. This one is this. Now, I'm not asking you to remember this. I think this is only 1 mark maximum, possibly only half a mark. So I think it is too complicated for many people to remember, but that is what is forming copper ammonium, sorry, ammonia. And it's 2 plus overall because the copper is 2 plus and the ammonia is not charged. Okay, so that's what happens in excess there. Okay, so I'm just going to get rid of that. Now the last one is the ammonium. In ammonium, if we add sodium hydroxide, the first half of this table is sodium hydroxide here. So all of these are sodium hydroxide. We get no precipitate, but on heating we get ammonia gas. And what is happening is this. Let us take NH4 plus. When I add sodium hydroxide and I warm it up, the OH minus reacts with one of the H pluses to make water and ammonia. Now, ammonia is a gas, so it is given off. Okay. And this is the question which we started today with. How do we test for ammonia? Ammonia turns damp red litmus blue. Now I'm going to get rid of that. I'm being a bit harsh today. I'm going to stop sharing. And I ask people to write me an equation. Okay, are you ready to write an equation? So the first one is, how would ammonium become ammonia with sodium hydroxide? So I have ammonium. Let us say I started with ammonium chloride and I add sodium hydroxide. When I warm it up, it gives off ammonia. How? Can you write me an equation that produces ammonia from ammonium? So I'm starting with ammonium. What is the formula for ammonium? I'm going to add OH minus to it. What forms? Mathari got the answer? Who can show me the answer before I show you it? This is a test whether you were just paying attention or not. Pressure is on. Kabira is so scared that they are standing up. Mathari mixed. St. Mary's. Yes. Well done. Okay, I'll write it down. Here we go. Before I do the last bit. So this is, you have to remember, it is ammonium. is Na. Oh, hello. What is happening here? NH4 1 plus. When I add, what is happening here? When I add OH minus to this, the ammonium, which is actually NH3 joined to H plus, the H plus goes with the OH minus to form water and ammonia. That's the gas which is produced. The second question is, can anybody write down the chemical which is present in the dark blue solution up here? What is the deep blue solution? Oh, my pen has disappeared. I don't seem to be able to write on my screen at all. That's a bit annoying. Okay. Ah, here we are. Here, what is something very strange is happening here. Ah, there we are. What here, up there, can anybody write me the formula for the chemical which is formed there? Anybody tell me the formula for the chemical which is formed there? No, it's not. Ah, I'm talking about after with the excess. So we form a light blue precipitate, which is CuOH twice, CuOH2. And then when we add excess, it goes dark blue solution. What is in the dark blue solution? What is the chemical in the dark blue solution? What is the copper containing one in dark blue solution? Anytime it redissolves, it will be in square brackets. It's a very good idea, but it's not that. Dandora, it's not that. Don't worry, don't worry, don't don't let yourself down. It Copper does not redissolve in sodium hydroxide. If something redissolves in sodium hydroxide, it is always OH4. But in this case, it is something different. I'm going to, so I can move on, I'm going to write it down so you can all see it. And we're just coming. Here we go. It is Cu reacts not with OH, but with ammonia. Same pattern, so there are 4 of them. And it's in square. For some reason, my pen is disappearing. 4 of them in square brackets. And therefore it is 2 plus because ammonia is not charged. So this is the blue solution afterwards. Okay, let's move on. So we have done amphoteric. Amphoteric are the ones which redissolve in alkali. Okay, the ones which redissolve in alkali. Your teacher will get this, which is something that you can watch. But basically, it takes iron 3 hydroxide and aluminium 3 hydroxide, as it says at the top, and it adds nitric acid to one and sodium hydroxide to another. Nitric acid, sodium hydroxide. I'm just going to show you the result of this. We're not going to watch it. Here's the result. So, oops, sorry, go back just a little bit. Okay. So at the end, when you have added acid, the precipitate dissolves. When you add alkali, it does not. But aluminium, when you add acid or, I'll come back, acid or alkali, it dissolves. Okay, that's important. So I'm just going to mention that very quickly. Oh, come on, move on. So here we go. So if I have something which is amphoteric, like zinc, so if I get the white precipitate, we already know that with alkali, I add OH, I add two of those, and it makes ZnOH4, 2 minus, and that has redissolved. But, so, oh, hello, what has happened here? That is, that's with an alkali. What would happen with an acid? Well, with an acid, it's much easier. We get ZnOH2 plus an acid, H plus, and I get zinc ions and water. Now, sometimes they want you to write it with a particular acid. So, for instance, zinc hydroxide and nitric acid. And they expect you to write zinc nitrate is formed and water. Sorry, two there, two here. Okay, so that's with the alkali. We get this, what we call complex ion, and with an acid, it is just doing this ordinarily. Okay, so if it is not amphoteric, it won't do the top one. That is amphoteric only. And the amphoteric only ones are the ZAP. Okay, all right, moving on. I'm not doing that. Okay, I just want to give an idea to you. I want to show you something that I tell my students because you are getting to the point where you should be doing past papers, questions, and so on. I don't know if any of you do this already, but my students have what we call flashcards. They are little cards where we put a question on one side and the answer. What's the answer to this? If T plus OH minus gives a green precipitate, what is T? T is iron 2, Fe2 plus. And this way, if you get with a friend or several friends or your school or whatever, your chemistry class, you could each produce some of these and then you could share them and you can use them to test each other. So if you know you are doing analysis, you could say, hey, if I've got an unknown and it is Fe2 plus, how would I test for it? And the answer is I would add OH minus and I would get a green precipitate. So X gives a white precipitate. It does not dissolve in excess. What could X be? It does not dissolve in excess. What could it be? The answer is magnesium or calcium. Magnesium or calcium. How would I test for magnesium or calcium? I would add sodium hydroxide. I would get white precipitate, doesn't dissolve. Do you see? If I add barium nitrate to something and I get a white precipitate, what is it? What is the chemical if I get a white precipitate with barium nitrate? It is a sulfate or a sulfite. Sulfate or sulfite. How do I distinguish between sulfate, sulfite? I add acid and this precipitate disappears. I add iodide to an unknown. It gives a yellow precipitate. What is the unknown? What does the unknown contain?
Potassium.
Lead.
What? Make sure you
It contains lead. Okay. Now, I heard somebody say potassium. Now that's okay because what they were thinking was P. So they're nearly there. Let's see PB. Ah, yes, it's lead. And then how do I test for lead? You see, I can turn the card round, use it the other way round. So how do I test for lead? I add iodide, it makes a yellow precipitate. I ask somebody to write equations. Zinc plus hydroxide. What will happen when I add drops and what will happen when I add excess? Can I write the equations? Yeah, the first one will be just zinc forming the ZnOH2. And in the second one, it is forming ZnOH4. X, I add ammonium hydroxide to it. I get a pale blue precipitate and then a blue solution. What is it? Now, these are really, really easy to make. Really easy. Just cut up some paper or some card. It is better with card. They last longer. Get with a friend. Say, I will produce all the ones on analysis. You produce all the ones on alkene, alkyne, alkane, alkanol. Okay? Produce lots of little questions and it will help you to revise. It is very, very good idea. Honestly, my students use it all the time. Some of them, by the time the exam comes, they have 100 of these little cards. It is really good. Quick test, quick test. Okay? Right, but now it is the end